Is this working? Yeah. Can you hear me all right? Well, my name is Joel Barnes. I am from Prescott, Arizona. I'm a faculty emeritus at Prescott College. Um, More recently, I'm more involved with my little LLC called Riparian, Restoring Watersheds, and that's one of the reasons I ended up crossing paths. One of the many reasons Larry and I crossed paths. Larry's the founder and director of the Spring Stewardship Institute, and does this guy need an introduction? He's wears many hats, but this morning, in this moment, he's the founder and director of the Spring Stewardship Institute. And this morning, we're going to talk to you about springs in Grand Canyon and some of the connections between springs and tributaries. So what we want to do this morning, Larry and I, we want to help you as guides share with your passengers and each other the ecological and cultural significance of springs and tributaries. Yeah, I'm looking away, right? Yeah. So we want to help you as guides share with your passengers and each other the importance of springs, both from a cultural and ecological perspective. We want to share with you how these springs are connected ecologically with their tributary mouths, and then we want to help you reconnect with why Grand Canyon springs and tributaries deserve to be studied, protected, and respected. So some of this is reminders and for us all to kind of collectively connect with the importance of springs and tributaries. So there's over 1,400 springs in Grand Canyon. Is that the highest density in Arizona? So it's deceiving to think that Grand Canyon has the highest density of springs in the state, but really it has to do with this, the hydrology and geology and the biology and ecology of Grand Canyon. Now, extremely diverse, the springs, when you look at them collectively. They range from these gushers to these whisperers and everything in between. And we visit these springs every trip. We take our clients, our passengers to the springs. So while these springs really comprise just a fraction of the landscape, like 1.3%, yet they support upwards of 30 to 80% of Grand Canyon's biodiversity. So they really are an ecological bottleneck. And when you look at them collectively, even closer, they represent the 7%. They contribute a whopping 7% of the Colorado River's flow. They're also highly valued cultural sites. They're sacred and life-sustaining. So springs emerge wherever groundwater is pulled by gravity to the surface of the canyon's complex and vertical landscape. So springs really represent a moment where groundwater becomes surface water. And it's significant. It's monumental. I mean, that groundwater has been on a journey. And when you're there in that moment, you're experiencing that transition, that emergence from groundwater to surface water. And this pathway has a lot to do with the dynamics and diversity, temporally and spatially, of Grand Canyon springs. So 12 types of springs found all over the planet, 10 of them are found in Grand Canyon. So that pays heed to the diversity, both topographical, geological, and hydrological of the spring story in Grand Canyon. So these are some of these are 6 of the 12 spring types. Here are the other 6, and the only 2 we don't find in Grand Canyon are geyser and exposure. And we actually, if you're interested, have a handout that's been adapted from the Park Springs website that has all 12 or 10 of these springs and examples of each of these springs in Grand Canyon, so you can passengers know to connect with spring type sessions and visit them. So again, Grand Canyon Springs hydrology and structure are directly connected to its complex geology and its vertical topography. That gentle tug of gravity that pulls it out to the surface of these thousands of Grand Canyon walls, and that's where these springs. So springs are dynamic. Springs are dynamic from a hydrology, geology, biology, and ecology perspective. And they're diverse in terms of their recharge source. Where did this water come in? What path does it follow? What geologic matrix? What are the rocks it's been flowing through? And how much time has it spent with each layer? What about the biodiversity? Once this water has emerged, what kind of aquatic and riverside or riparian biodiversity do you find there? And what about the water chemistry? That's also highly diverse from one spring to another. And of course, the discharge rate or outflow rate also is a significant component of spring ecology. So these components here all kind of synergize to create dynamic conditions from spring to spring. In terms of water, in terms of water quality, temperature, dissolved oxygen, and isotopes, responses to pollution and climate change and groundwater pumping. So responses to groundwater pumping can be a matter of decades or centuries, depending on the spring and this residence time or flow of the groundwater. There are obviously hotspots for biodiversity and individualism. So some examples of springs that we all experience with our planet. Basis Paradise, so it's a gushing spring. The base flow comes from the North Rim, and the groundwater flow path is anywhere from hours to decades, and it's about 15K from the North Rim to where it emerges here. And you can see that, back in the 80s and 90s and even early 2000s, Basis was gushing. It was really gushing. And now, since then, even in 2018, it's much less than it was decades prior. And now it's even less than it was a decade ago. So Basis Paradise actually does have a much kind of a relatively quicker response for precip events and seasonal and decadal events. So interesting contrast there. Pumpkin Springs, another good example of a spring we pass on every trip. It's a mountain spring, and the base flow comes from the south rim. The flow path is probably thousands of years. That means it's a slower response time from source conditions and events like groundwater pumping and precip. Because it's been so long in contact with geologic matrix rocks, it has high levels of arsenic, lead, and zinc, and there's virtually little or no macroinvertebrate level. You don't spend a lot of time in springs, but you do see pictures from decades ago of people hanging out in the springs. So let's compare that to the Fence Fault Springs. It's a rheocrine and hill slope spring, which means it flows directly into the river. And the base flow comes from the north and the south rims. The discharges, there's actually a set of springs on both sides of the river. And so some of that water that comes out of Fence Fault actually is flowing under the river. The flow path is undated, but some studies by or Crossing Company really based on recent data from these studies and how they reveal steady temperatures and isotopes suggest a longer flow path. So you can see how the springs vary from spring to spring in these conditions. So not only are springs important from this hydrogeologic ecology perspective, they're also clearly really important from a social point. We talked about the emergence of groundwater into surface water. And there's also an emergence from an indigenous perspective. Again, springs represent a moment, and it's an important moment from an indigenous perspective. And the Hopi Seco pool on the LCR is a classic example of how traditional cultural properties really are places that indigenous cultures maintain and pass on cultural beliefs and traditions, and they're focal points for ceremonies and connected with ancestral spirits. They're also essential water sources for indigenous life and agriculture, like here in the Springs offer us as guides opportunities to use as a recurring theme in our trips, sense of place and an indigenous presence in the landscape. And it is common to associate living mindfully in a bioregion as an important piece of sense of place. Living mindfully with the seasons, the climate, the soil, the topography. And that's all really important. And springs help us to take that added dimension to that sense of place to not only a sense of place in a bioregional sense, but a sense of place in a specific spot. And again, they are places of resources. And it's important, as you already know, and this is us reconnecting with this important, to really help your passengers approach springs with this holistic awareness of the importance of springs from a scientific as well as an indigenous perspective. And it's great to frolic and play and sing around these springs. And you want to do that with the foundation of respect, humility, and reciprocity. And that's really the foundation that we should bring to these springs. Because the energy you bring to these special places, leave a sliver of that there. Everyone who goes to these special spots, these emerging spots, you leave a little bit of what you brought. And so help your passengers to bring good intentions to these spots, because that's what they leave there. And so these springs are important from a more of a, I guess, measurable scientific perspective as well as cultural. So in the context of the canyon's arid and bioregionally or bioculturally rich landscapes, its springs and seeps are critical life-sustaining resources that deserve our respect and protection. And again, these are kind of reminders for you as guides. And what Larry's is going to share with you now is some the results of some recent research he's done on how springs are connected to tributaries and tributaries.
Thank you, Joel. That's a really great introduction to where the water comes from. And what I'd like to do today is talk about how it reaches the river, what that story is about. We have a couple of co-authors on the work, Joseph Paulay, Peggy Ellsworth, and Novelist. Grand Canyon River Outfitters Association funded a lot of work as did our national labs, and Grand Canyon Youth was just fabulous in terms of providing us with support for this work. So these are bugs that live in tributaries. Some of them, we have a wide array of species in these streams. Tributary streams are often very different than the main stream. So understanding why these things are in the tributaries but not in the mainstream is a kind of a big deal, because these are often fish food. The fish are all that are important to a lot of people, and we're left with trying to figure out why we have this big discrepancy. We looked at 24 sites through Grand Canyon, looking at tributaries. And again, these are important because these tributaries that we go to are among the last pristine streams left in the Southwest, maybe in the West. Very few pristine desert streams exist now that haven't been grazed or mined or otherwise kind of tortured by human activities. In going through these sites, what became apparent to us is that we've got two processes that are shaping the way the insect life lives in these things. We've got a process called cementation. The stream has a lot of calcium carbonate in the water. The stream floor will become cemented. All the aquatic invertebrates we're looking at there really need interstitial space in the graphics. When the stream floor is cemented, there's no interstitial space. Similarly, in the mainstream, the gravels and cobbles there are usually embedded in sand. And so that is also kind of a barrier to aquatic invertebrates, because there's no place for them to sneak down to when the flows change. So we have this situation of two gradients there. If they're combined, we have very low species richness and diversity. If you have neither cementation nor embeddedness, which is typical of places like Tapeats Creek, you have very high invertebrate diversity. A bunch of you have participated in the citizen science bug work, and this is addition, not an exception to that work, but in addition to understanding that the distribution of water levels. So again, this picture just shows that you've got diverse kind of low, medium, high levels of sedimentation and cementation in the tributaries, but largely a sand-dominated basin. So, get in the water. We had great Greg Kenny youth participation in this project too. Kids and cooking bugs in water is just the best. Really, really fun. Streams like the Peace Creek have lots of interstitial space, gravels and cobbles, not much sand. And because of the relatively low levels of calcium carbonate in the water, the cobbles are not cemented. So this is a place where we see a lot of bugs. In contrast, the mainstream there, this is kind of a normal situation. You see rocks embedded in sand, just pure sand, and or very fast flowing situations that don't really have a lot of interstitial space. Looking at the water temperature, a couple of parameters there. Looking at temperature, yeah, the tributaries they vary seasonally and across the year, and not much difference between the river. Tributaries and the river there, tributary miles here. Tributary miles, the pH of the water pretty consistent within streams and variable enough that it matches what's going on in nature. The big differences that we found in water chemistry had to do with the amount of salinity in the water. Again, think of very, very salty streams like Lava Chuar, which you drink that, never in a million years. You can actually see the salt crystals forming on the surface of that. And places like Pumpkin Spring, just saw pictures of their really pretty mineral rich systems. So lots and lots of variability compared to with streams like the Peace Creek, for example. River goes up, pretty consistent level of specific conductance or mineral around 750 microsiemens per square. Well, so we developed a metric of discontinuity. Discontinuity is the difference in bugs in the stream, in the tributaries versus the main stream. So what's in the creek versus what's in the mainstream? Doing that comparison at these sites allowed us to identify situations in which the tributaries were very rich and the mainstream was very low. That gives us this metric of discontinuity of a value of near 1. Where the mainstream has more bugs in it than the tributaries do, is a value of -1 in the Pumpkin Spring there. What struck me immediately with this was, well, this is not a kind of a random distribution here. We've got these karstic springs that come out in the middle of the canyon that are like the Peace Creek, Shinnemoo, Bright Angel Creek, that are places where there's a lot of aquatic life in the streams. And those are places with low cementation and low fine sand. Those are in the middle of the canyon. Downstream, both upstream and downstream of the middle parts of the canyon there, we have streams like the Paria in the upper basin, LCR, and places like Pumpkin Spring down in the lower that are very rich in minerals. And so lots of cementation of the streams and very little invertebrate. And that factors in just exactly as we predicted with our kind of conceptual model. There is that our biggest diversity of aquatic bugs are in places with high water quality and good water quality and low amounts of embeddedness. And those sites that have both high values of each of those variables are very, very low in the what also got us going with so we looked at tributary mouth environments in the number of species per sample in Grand Canyon, comparing that with what was in Glen Canyon from Woodbury's work in 1959. Woodbury found that the mouths were actually pretty low in diversity, and here we now have a higher diversity of bugs in our tributary mouths. Is that a fair comparison? We don't have any data on aquatic bugs prior to the damming Grand Canyon, but we have this very interesting kind of comparison here, showing us that tributary mouths may have increased in biological value over the course of time. And we see this at the Beach Creek with very detailed studies from previous work that we found the two mouth channels that had higher biodiversity when we put in these experimental samplers than did even the creek or certainly Main Street. So the creek mouth can support a lot of life, and post dam time that may have become more important, much more important factor. All right, so our conclusions here are that these discontinuities are and were probably common in both like landing and granting. Seededness and embeddedness reduce benefit of macroinvertebrate richness, assemblage complexity, and that means that having loose gravels and cobbles provide benefit perfusia for these aquatic bugs. Our conclusion from both papers is that we cannot simultaneously manage for fine sand and rich aquatic invertebrate assemblage in the main stream. Anyway, thank you very much. And
We have a couple of questions if you want.
yeah, please.
Couple questions?
Yeah, I was with you until that last point.
Oh.
I think it's the way.
So
The conflict.
again, embeddedness of gravels and cobbles in fine sand is not good for aquatic invertebrates. They don't have refugial space. And so if we're managing for a good mass balance of fine sand, that will prevent those kinds of invertebrates, not midges, but those kind of bigger bodied invertebrates from being able to live in the river. Yes, we have a couple examples of species that are specially adapted, perhaps in the mainstream, but relatively few. Go ahead.
But managing for sand doesn't mean taking sand into the ground. Maybe it means using high flows to remobilize sand, and potentially scour sand into the ground, do the opposite. So managing for sand is not simple putting sand everywhere.
Absolutely, and it's a reach-based phenomenon, Paul, because more aquatic invertebrates in the least area Glen Canyon reach than we have downstream. So those are important kind of factors to bring in. What can we get with aquatic invertebrates? Yes, we might be able to manage for more midges, but these larger body forms they're really challenged by having that embedded by being embedded just in fine sand.
Right. And sand is coming in all the time. And then the flows we can manage the sand with the opposite. We pick it up and move it. So I understand the connection between sand and benefits and bugs. But the connection between what the dam is doing is how we're managing the sand. I think might be
Good. So as you can see, there's a lot of discussion still to be had about this. Science is not a perfect process. We're still improving our data in this with some great suggestions from GCMRC, and there's more to talk about. But trying to bring up this point, which is very apparent from looking at the bug seeding tributaries.
Another question?
Yep. What's the last part of it? Yeah, so fluctuating flows are also playing a role in this. As Emily was pointing out, fluctuating flows can have positive as well as negative effects, and trying to tease that story apart is kind of a big deal. I can refer you to this paper we did on the Peach Creek, where we very carefully looked at stage variation over time, and that paper showed pretty clearly that fluctuating flows were a partial driver, but this really the issue of having interstitial space refugium, which we experimentally demonstrated by putting gravel baskets in the river, and those were actually downstream to Peach Creek. Those were actually colonized by some of the bugs that live in Peach Creek, which didn't otherwise occur there. So good direction to that paper. Yeah.
Thank you very much.
Oh yeah.
All right, next we're gonna hear from Kat Cooney from USGS. You want to stand? Okay, cool.
Pat, will you stand, like, will you like kind of be right here?